Okay. Yes, sorry for the delay. So today I'm going to talk to you guys about explainability or interpretability. Hopefully it can be generalized enough that if you want to apply it onto others field. But mostly today we're going to focus on transformer and specifically transformer on natural language processing task. So first, maybe I want to distinct a bit between the terms of explainable AI and interpretability. So explainable, it's somewhat more broad terms. And within explainable AI, there are multiple dimensions. So the first dimension is that we look into model agnostic methods compared to interpretable models. So model agnostic methods are the methods that helps you to look into why a model make a certain decision, why you don't really need to have the understanding of the internal working of the models. You can just simply treat the models as black box. So for example, like the LAM method, where you just simply try to perturb the input and then see what happens to the output. So just using the model as it is. And then this would be suitable to be applied on methods like support vector machine or deep neural network, which is usually too complicated for us to just look into their hundreds of weights and then try to understand. The other dimension, and now we come to the term interpretability, is that when we try to look into models that can explain themselves. So the easiest case is linear or logistic regression, where you just simply have a linear layer, and then each position in the input is multiplied with each weight in the linear layer, and then you have the output. And then just by looking at the trained weights, you can see exactly how important a feature is just by checking how big the magnitude of the weight that is associated to that feature position. Or you have decision trees. Decision trees, I guess, is even more straightforward because technically is something that you can it's even existing in real life when you maybe want to fix a fridge, and then you can see which decision to choose depends on which constraint. The problem is that for more simple tasks like classification with like sentiment no, maybe it's not. Yes, so for more simple tasks, maybe linear regression or decision trees is enough. But for more complicated tasks like text generation, like with large language model recently, it's not really feasible to use such simple method. And then recently, people have been looking into, can we make transformer more interpretable? And this is quite an ambitious goal. But in this lecture today, we can see that what is the progress so far in the field and whether we can confidently state the claim that, okay, transformer is interpretable. So that's the main distinction between explainable and interpretable. So explainable is more general. You want to be explained why the model does this. But interpretable is more related to the model itself. Like, can we just make something out of the weights of our trained model? Another dimension of explainable AI is global versus local explanation. So global is when we try to see what the model have learned overall, which I guess we can also read from decision trees or linear and logistic regression as well. But local is how an individual prediction was made. And that would be the main focus of the lecture today as well, because yeah, for a huge model, I guess is already ambitious to look into the local explanation, and global would be something that is quite difficult at the moment. So as mentioned, I would like to focus mostly on the transformer architecture because it's still state of the art, and then all LLMs use it, well, mostly. Yes, so this is the unroll plot of the transformer architecture. So these are the different input steps. So this is just simply unroll, and then this is what you have known before, that the transformer just do auto-regressive prediction, taking the input from the previous step and then gather them and then predict the current token. So in short, in a transformer, we have the embedding layer, which is in this position. Somehow they are not denoting it, but yes. And then there's two main components in transformer is the attention block, and then followed by a feed-forward block. And then by the end of all the attention and feed-forward block, we would feed the last hidden state into an unembedding layer, which is a linear layer which just projects this last hidden state into the vocabulary size vector. Then you will have your logits, which is not yet normalized. And then you need your softmax in order to force those logits into a 0 and 1 range. And then you have probabilities, and you can simply just sampling from it to generate your text. Another factor in this architecture is that usually we have a layer norm component. In the previous more early implementation of transformer, usually people put this layer norm component after the transformer block, which means that they would, like here you can see this is the attention block, and then usually they would put it after this block, so directly onto this hidden state. However, this is later show that it's not very good for interpretability. I don't want to comment on the performance, but it's not that good for interpretability, because the alternative of that is to do layer norm before this attention block. So which is so-called pre-layer norm, which is later on implemented in more modern architecture. So for pre-layer norm, you do this normalization before the attention block. And then you can, so with pre-layer norm, you can see that after an attention block, you have some output, which you just add up to the residual stream. So this directly relates to this definition of residual stream, because as you have learned from Jan's lecture, probably that in transformer, we have this residual connection where you just directly concatenate the input of the previous state into the output of the new state. So by doing pre-layer norm before this attention block, we are not distorting, we are not stretching or shrinking the flow of the representation. So this whole multiple blocks and layer can be interpreted as multiple addition to this one main residual stream. So this helps for interpretability, because later on you can see that thanks to this factor, we can see exactly at which component contribute how much to the final prediction. And then it's easier to understand, okay, what is the function of each component of the model? And some people have shown that pre-layer norm is a bit more stable to train, that it leads to exploding gradient less, but I don't have exact experiments and experience with that. But yes, so transformer recap, embedding layer, attention block, feed-forward block, unembedding layer, softmax, and pre-layer norm either before or after. And if before, we can call it residual stream. So that's a quick recap of transformer. And now we will go to the different techniques for interpretability. So there are two main branches to interpretability. The first one is that we try to localize to see how much does an input contribute to the final prediction, or how much does a model component contribute to the final prediction. Another branch is to try to decode information from the model representation. So as you know, there are multiple hidden states after each attention or feed-forward block, and then we try to, just read something from it. So first we will talk about the localizing part. Yes, so the first method for localizing input is to look into gradient-based input attribution. So for this method, we would need to create, so for this input X, we would need to create some kind of baseline to see that if X slowly move to this baseline X prime, then what will happen? Usually people just choose this baseline to be the zero embedding. And the idea is that we try to calculate the integral of gradients along the straight line path from the baseline X prime to the input X. Then the contribution of the input token at position n to the output token at position n is then defined at this formula. If you just look into this, you can kind of intuitively see that this integral, the alpha, is going from 0 to 1. And here you have alpha x minus x prime, like x prime plus alpha, and then this formula. So you can imagine that as alpha going from 0 to 1, x prime is, wait, 0. X prime is slowly moving. No, x is slowly moving towards x prime, and then we can calculate what is the changes to the gradient if the input change into 0. And then we can see how important that input feature is to our model to make the current prediction. So that's the first one. So that one was looking quite into details of the gradient of the model. The second method is just to do perturbation-based input attribution. And there are multiple different ways to do input perturbation. The most simple way is to simply remove the input token from your input sequence. However, the problem with this is that usually text is discrete. And if you have a sentence and you just simply remove one word, then your sentence will not be natural anymore. It's going to be some very abnormal kind of input. And it's unlikely to happen in real case usage. So another method is to replace input token with some alternative. For example, you can use BERT. BERT training objective is language masking. So technically, if you just mask the input token XM from the sequence, you can just straightforward using BERT to find different alternatives to that token and to fill it in. And then you have more natural sounding perturbed input. That's the first step, input perturbation. And then after the perturbation, you would measure how much the output change after you perform such perturbation on such input. One way is to check whether the output at the time step Tn changes or not. Like, does the model still choose to output this token or not? But then it would be looking at the output in quite a high level, because what if the model still strongly wants to output this one token, but just because the input change, it select another token, but then the probability of the original token is still relatively high. So another more fine-grained method is to check the resulting probability difference. So is the model now much less confident on outputting the original token or not? So yeah, just checking the subtraction. Yes. Okay. So I guess one limitation of this method, perturbation-based, is that you first of all have to create multiple version of perturbation to be sure that you're not accidentally creating some kind of bias while creating the perturbation. And the second thing is that you would have to run your model multiple times on multiple perturbed input, and that can be costly. Okay, and now we come to the next method, which is context mixing for input attribution. So we want to see how much does one input token contribute to the output token after one attention head. So one way is just to directly look at the attention weight. So if the model assigns high attention weights into this one position, then probably that position is important. However, this approach is not optimal because how much an input contributes to the output doesn't just depend on the attention weight, but it also depends on the magnitude of the value of the token itself because it's a multiplication. It doesn't just depend on this value, but also depends on how big this value is. So another method is to do output value weighted vectors. So trying to take into account also the magnitude of the vector. And then another method is to calculate the distance between these vectors and not just simply the magnitude. Yes. Any question so far? Okay, if not. So in the earlier days when transformer is not technical, I'm not sure if it's transformer or not. Okay, but in the earlier days, the architecture of the attention is a bit different because back then we have encoder, decoder, NT models with one mechanism of attention only in the decoder. So we only have one attention layer, and then the decoder decide which parts of the short sentence to attend to. So with the simple architecture of attention, we can just simply do this previous method and then understand directly how much an input contributes to an output. However, nowadays in modern transformer models, it's not like that anymore. We now have multiple transformer layers in both encoder or decoder only. So technically in every position, in each layer, all of the information of all input is kind of mixed. So if you only look at the attention score from one layer, it doesn't exactly show you how important an input is because it only shows you how important this representation is. But then that representation is already mixed with all the other ones in the previous layers. So bottom line, you cannot just simply directly use the attention score. And that leads us to attention rollout. So so here's the formulation. People have shown that there's a way that you can kind of reformalize the attention head so that this is the representation output after the attention head. And it's going to be the sum between all the input representation in the previous layer plus some value. So in order to calculate how much the input token at position J contribute to the output token at position I after only one layer, then you can simply just take the subtraction and see how, and then just normalize it to see how much this input contribute compared to the whole input sequence. So that's only after one layer. Attention rollout, what we need to do is to gather the contribution throughout the whole transformer model. So you have to go through every single layers and see, okay, at this position, this input contribute this much, and then you accumulate the contribution of that input over all the layers. So yeah, as mentioned here, the information flow in the model is modeled as the directed at cyclic graph. The nodes would be the token representation, and the edge would be the token to token contribution. So what we calculated here. And then the final contribution would be the sum over different paths connecting both the input and the output nodes. And the value of the path is the multiplication of every edge in the path. So as you can see, because we have so many layers of attention and self-attention and cross-attention between encoder and decoder, we need to do some sort of gathering like this to see exactly how much one input contributes to one output on the surface level. Okay. So the next method is contrastive input attribution. So for this one, it's not necessarily a new method that is independent from the other ones, but it's just simply an add-on that you can easily apply it onto the previous method. So so the problem that people have seen is that transformer models, sometimes they have this kind of recency bias that is always focused the most, like when doing next word prediction, is always focused the most onto the token that is right before. So for example, if you look into this example, so if the question is why did the model, if the input is can you stop the dog from, and then our question is why did the model predict barking? If we just simply look at the token contribution and the attention itself, we will see that most of the attention is focused on the word from. And intuitively for us as a human, it doesn't really make sense. Like if the model predict barking, we would assume shouldn't it come from some other word like stop or dog? So yeah, so if we just simply use the attention, we can see that there's some bias and then maybe it doesn't make sense. And what people have proposed is that instead of asking one single question, why did the model predict barking? We would do it like contrastively. We would try to ask, why would the model predict this but not that? Why did the model predict barking instead of crying? And why did the model predict barking instead of walking, for example? And the way people have been doing this is just simply take the difference between the attention when the model predict barking compared to when the model predict crying. So just with some comparison, then now you can see that the results somewhat make more sense, that it focus more on the word stop and off. And as I mentioned before, this is not really an independent method. It's just simply an add-ons that you can simply combine with gradient-based or attention-based methods. Okay. And now we would look into this in somewhat a bit different aspect, that instead of trying to just look into the immediate input and see why did the model predict this output, we would try to look at the whole training data. Did the model predict this output because it has seen something during the training process? So the name of these branch is training data attribution. The goal is to identify influential training examples that drive the specific model prediction at inference time. And then with this method, maybe we can detect unwanted bias, like, for example, woman associated with nurse or something like that. And then we can just remove them from the training data or make them more balanced. And as a side, if I can use it for data cleaning. So the approach here is to run multiple training simulation where you just take subset of the training data and train the model and then see how the model behavior changes. The limitation here is that is extremely inefficient because you can imagine having to train a model multiple times is a lot of work. And then having to kind of predict ahead what kind of bias it can be so that we can try out multiple simulation with multiple subset of the training is also a lot of work. So people have been doubting the actual applicability of this method, but it's a nice proof of concept just to see how important training data can be for a model. Yes, any question so far? Okay. So the next method is to look at the logic attribution. As I have mentioned in the recap of transformer architecture, if we do pre-layer norm, we can adapt the residual stream mindset. And then we can think of every contribution of each component, like the attention also, as the addition onto the residual stream that go directly from the input to the output. So this is so-called logic attribution. And then we would consider multiple attributions. So there's this direct path coming directly from input to output, the full OV circuit, which takes in the width values from the transformer and see how much it contributes to the output. And then we also consider this, what they call in the literature, virtual attention head, because we cannot neglect the fact that different components also interact with each other in some way. So if we just consider the contribution of each component alone to the residual stream, maybe it's not enough. Yes, so there's that 3 components, and then we can see how much it changed the final logic, and then see where the components play a role in the final prediction. Yes. The next method for localizing model components is to do activation patching. So here we just simply create a patch, as in we try to, so this is the residual flow. This is the rollout transformer architecture. And then we try to just simply corrupt one component in the model and then see how much it changed the final prediction. So there are multiple ways to create this kind of patch. One way is to create some counterfactual data set, which we just include some sort of adversarial training samples, which is simply wrong, which have like, some input signal regarding the task are simply inverted. So it's just some wrong samples. Another way is just to create this, replace this patch with zero vector, or replace it with the same thing, but then we add some artificially created noise like Gaussian or so. There's pros and cons to each of these methods. So to create the counterfactual data set, I mean, we probably need human crafted data, which might be costly to consume. And for zero intervention and noise intervention, if we just naively replace one patch, one component with zero or noise, then we lose the naturalness of the model. Like it's kind of similar vibe to perturbation model. If you just simply remove the token, then it's not natural anymore. Here's somewhat the same. If you just remove this one patch with some roughly noise or zero vector, then it's just simply not the natural flow of the model. And maybe your analysis of the model would be quite biased. Like the model wouldn't have done this if you hadn't created such an unnatural patching. Yes. Okay. So I guess that might be all on the single component. Another branch of interpretability is mechanistic interpretability. So this has been quite a famous research area recently, where people try to reverse engineer neural networks into human understandable algorithm. So they try to just look at the neural network model's weights and then see, wait, does this weight in combination with each other actually do some algorithmic procedure that we can understand? So the focus here is to uncover the existence of circuits. Circuits is subset of model components which interacting with each other to solve a task, which I guess I can show later in the lecture. But usually it should be like a combination of, for example, 2 attention heads with each other working together to find out that, okay, in this output, we should have copied the previous or something like that. To discover this kind of circuits, we can use the approach that we have already discussed, like logic attribution, activation patching, or edge and path patching. So not just simply the activation, but we also patch the edges in the models. The limitation here is that it's quite difficult to detect these circuits because it requires human to actually look into it and see how the model behaves. And it would also require domain knowledge of the task that the model is trained on. Another huge limitation is that some people have found that transformer model might have the ability to do self-repair. So if you just try to corrupt the activation at some part in the model, maybe it would be able to recover afterward because there are multiple layers in the transformer. And then simply your corruption might not affect the model in the end. Yes, so that's the issue. Okay, so I guess that's the first half on focusing on localizing. How much does what component contribute to the output? The second branch is to try to see if we can extract any information from the representation, from the hidden representation. Any questions so far, though? Yes?
Is self-repair caused by dropout? And if so, could you avoid the problem of self-repair if you just avoided dropout in the training?
Yes, that's a good question. I haven't read about it in the literature yet, but I can assume that maybe dropout is an issue. However, I'm not sure if it will completely solve the problem if we just simply remove dropout, because many people have shown that deep neural network model like transformer, for example, they are really sparse. It's like when you run the model, not every single neuron is always active, and then not every single weight is always actively used. So even if you don't do dropout, maybe the model is already just taking partially rest somewhere in the model that we don't know about. And then maybe it would still have the ability to do self-recover. So yes, I do think that dropout is one of the issues, but I'm not sure if just removing dropout would be enough. Okay, any other? Okay, then we can come to the next. So the first approach to try to decode some information from the representation is to do probing. The idea here is that when we have, so X is the input and FL is the output of the model after layer L. So FL is just the hidden representation at layer L. We would try to train a single linear layer where we take this FLX as the input, and then we try to predict some labels, some attributes. This label can be the sentiment of the input, like is it positive or negative or aggressive? Or it can be something regarding to gender, just to detecting bias, like did the input talk about man or woman or something like that. So by doing this, we can try to see that at which point in the model did it start learning about this specific feature. However, the problem in probing is that people have been questioning, is the probe expressive enough to evaluate the information encoded? Because here it's just a single linear layer. Is it actually enough to tell whether this representation is learning this feature or not? So the question here is that why do we limit ourselves to linear probes then? Why don't we just use something stronger? I guess one answer is that maybe the hidden representation is already quite large, and if we have more complicated models, first of all, it's not that explainable anymore, and maybe it would take too much time to train. But the main reason people have been doing this is that they have this hypothesis that is called linear representation hypothesis, where they assume that features are encoded as linear subspace in the representation space. As in, they assume that they can always find some hyperplane to kind of separate different attributes of one feature, as you can maybe see. This is annoying. Okay, as you can maybe see in this figure. So here, I think the task is to see the sentiment of the different input, and one is positive and one is negative. And then the linear probes that is trained, that is output in the end with this kind of hyperplane. So with linear probe, we can have a hyperplane separating representation associated with a feature from the rest. So this line here. And the normal vector to that hyperplane, as if the orthogonal vector to that hyperplane normalized, can be considered as the direction representing the underlying feature. So this vector u over here, we can understand that is the direction that represent either positive or negative sentiment. And thanks to this, you can start modifying your model. So if you want your model to kind of ignore this aggressiveness in the input and just try to be nice in the output, you can try to subtract the representation by this normal vector. So like I said, I guess the main reason for linear probe is that it's very explainable. And then we can get something out of it to modify our own model to our interest. One problem with linear probing is that it can also just detect correlation rather than causal. That if the model just happened to be aligned to this one single features, then linear probes can detect it, but it doesn't really like explain the model predicts this because of that. So it's still somewhat like an empirical method that need further analysis afterward. So the next one is sparse autoencoder. So the main idea of sparse autoencoder is that you try to train an autoencoder that mimic the original encoder, that you try to reconstruct the internal representation while at the same time trying to promote feature sparsity. As in trying to promote that many entries should be zero. And by this, we also promote smaller feature activation. I guess originally, maybe this can be used to have faster inference time, because if you have a lot of zeros, then it's just simply less calculation when you run inference on your model. However, it's also useful for interpretability, because when the very important number of features is shrink down, then it might be easier for you to just look into it and then perform analysis to see what kind of features are there. So yes. Okay. Now we come to another approach, which is also intuitively quite straightforward, which is called logit lens. So the idea is to project the intermediate residual stream state after some specific layer by the unembedding matrix. So unembedding matrix, as I mentioned before, is that last layer in the transformer where you project the last hidden state into the vocabulary size. However, here with logit lens, instead of applying this unembedding layer on only the last hidden state, we try to apply it onto some previous hidden state. And by doing this, we can analyze how the model refines the prediction throughout the forward path. Because when you use the unembedding layer and then you just apply the normal softmax and sampling, you can see some actual output text that you can read. And then you can compare that, okay, if I just output already in this layer, the model is going to say this. But if I wait all the way until the last layer, the model is going to say that. This is also something similar to the early exiting method in literature. But I guess the motivation is different, because for early exiting, people just feed some intermediate representation into the unembedding layer and then stop. And the main motivation for that is that you don't have to run inference for too long. So if the model is somewhat certain already about its output, you can just stop at some early layer and then don't have to decode all the way to the end up to the other layers. So the motivation there is to save inference time, save running time. But here we're focusing more on analyzing how the how the model learns as it goes by in different layers. And before early exiting, there's another catch that you have to decide. That is, you have to decide at which layer should you early exit. Because if it's too early, then maybe the model haven't finished encoding anything. But if it's too late, then maybe it's overkill, and then you end up not saving time. And then there is some confidence method to analyze that. That is, if the model's logic probability is high already, then maybe we can stop here. But yeah, it's not really our focus. So the problem with logic lens is that the representation from intermediate layers are not trained to be passed to the unembedding layer. So technically, it has some very strong disadvantage compared to the last hidden state, because during training, the last hidden state is directly fed into the unembedding layer to produce the output, and then we have backwardation. But it has never happened for the intermediate representation. And one way to cope with this is that simply we can train multiple unembedding layers for each of the, like after each layer. Then it would be more fair, but of course we come with a cost that is more time consuming to train these unembedding layers. Because usually this unembedding layer is going to be very big. It should be like vocabulary size, because it needs to produce the logic for every single tokens in the vocabulary. So yeah, training this is not that efficient, even though it's just one linear layer. Okay, any question? Yeah, then the next method is to look into maximally activating input. So many people have had the question that, okay, the deep neural network model have so many neurons connecting to each other. Can we tell exactly the functionality of each neuron? And one way people have been doing this is to try to consider the input that maximally activates the neuron. If one input maximally activates one neuron, then maybe that neuron is specific to some function. And the way to create this input is that we can create it synthetically just by looking at the gradient of the model, or we can select it from pre-existing examples. This input can produce out of distribution behavior, and then people can just try to create inputs that makes the model produce unacceptable output. So this is what people also call jailbreak attacks. Yes. However, recent research has shown, does it even make sense to look at each neuron independently? Because it has been shown that, well, if we maybe ignore the layer normalization, then the residual representation are rotationally invariant. So it means that those intermediate representation, we can rotate them by an orthogonal matrix O, and then invert the rotation again by O minus 1. And then the output of the network is still going to be the same. So if you rotate the input and then rotate again, and then apply the weights of your model, everything is going to stay the same. Then this suggests that if you have a vector of representation of middle layer representation, if you look at position 0, maybe you won't be able to say anything out of it because it's rotational invariant. You can just rotate it and achieve the same thing. So it should not encode any specific features. But that is what happened in the residual stream. However, things are quite different for the feed-forward network block, because after we input the representation and I'm not sure if I mentioned this or you have learned before, but the feed-forward network block consists of 2 linear layers with one single activation, nonlinear activation in between. So after you input your stuff into the first layer, at this state, it would still be rotational invariance because it's just being processed by a linear operation. But then afterwards, thanks to the nonlinearity activation element-wise, like ReLU or gated ReLU also, then it's no longer be rotationally invariant. And thanks to that, we can start looking into different position of the vector and maybe trying to find out that, okay, maybe at this position is trying to encode like sentiment, or at this position is trying to encode some gender information or something like that. So bottom line, people have been thinking that looking at the representation on the residual stream, you cannot make too much sense out of the neurons. But if you look at the neurons inside of the feed-forward block, then yes, you can, thanks to this nonlinearity. Yes. Okay. But even when you solve the problem with rotationally invariance, we have this other problem of polysemanticity and superposition. So even though people have found that some neurons is associated with some features that is actually understandable and interpretable from human perspective, still most of the cases, most neurons just correspond to very random and unrelated input. So this is what they call polysemanticity, which means that maybe one neurons can encode multiple information and not just only one. The reason for this is that features can be represented as a linear combination of the standard basis vector of the neuron space. So maybe in order to encode the feature of semantic, of sentiment, instead of just using one single position neuron at 0, maybe it needs both neurons at position 0 or position 5 or something like that. And another problem is that models could encode more features than they have dimension, which is also called superposition, which means that it encodes more information than the dimension size that it has. So information is no longer like this one position encode this one thing and the other encode this one other thing. It's all kind of mixed. So it's still relatively to look into per neuron feature. Okay. Any questions so far? I guess that was all the interpretability methods. Okay, then I guess we can come to the last section. So thanks to those interpretability methods, people have found some kind of established patterns in current transformer models, which I will list as follows. So first, if you just look at the attention block, then people have found that there's some attention heads that is specific to some certain roles. So first of all is positional head. When they look into BERT, they find that some of the BERT heads attend mostly to specific position relative to the token process. So it's like it has one head that focuses to the token itself, one head focused onto the token right before it, and then one head focused to the token right after it. And recall that BERT is mask language modeling, so we can attain to future token. Another type is subword joiner heads, where it attains exclusively to previous tokens that are subwords belonging to the same words as the currently processed token. Because usually our training data is all subword and we don't just take the whole word and then, yeah. So there's some heads that have the functionality to just join them together. And then we have syntactic heads, which attains to tokens that have syntactic roles with respect to the processed token. So just, for example, like maybe I go and then it would focus onto the token 2 just to make it syntactically correct in the output. Then we have duplicate token heads, which attain to previous occurrence of the same token in the context of a current token in order to just simply copy over and output the same thing. And yes, copying head, I guess, is kind of the same, but it's more like on a subset of tokens and not just only one. And then we have induction head, which learns to increase the likelihood of token B given the sequence A, B, something, something A. So we have seen that in the input, A, B goes together. And then in the output, it would try to increase the probability of outputting B again after A. Then we have copy suppression heads, because copying is not always the best idea when you do language modeling. So for example, in this context, all sphere in love n, if it just simply copy and output the word love again, then it's not really a good choice. So these heads just try to avoid naively copying this content. And then we have successor heads, where in a sentence, if we have just a list of successing values like either counting number or like Monday, Tuesday, Wednesday, or January, February, and so on, then it would try to increase the logit of the token corresponding to the next element. Okay, so those are some of the patterns that people have found. And then we have this, it's not technically pattern, but it's just some interesting property of attention. People have found that, at least in BERT, many heads mainly attend to some special tokens like CLS, like the class token, or some separation token, and punctuation token. And I guess you can kind of intuitively think that this token doesn't contain that much information. Why would the attention head just focus on those tokens? And the hypothesis is that maybe a head attained to special tokens when its specialized function is not applicable. So it's like, okay, we have this input, but then within my capacity, within my capability, I'm not supposed to do anything with this. This is not applied to me. And then it just simply attained to random tokens as a form of doing nothing. And this hypothesis has been backed up by some observation where people see that the norm of the value vector associated with this special token or punctuation tends to be very small. So even when you have a very big attention weight, if you multiply with the small values of these special token, it would end up not having much effect onto the final residual stream. So it's kind of back up the hypothesis of attention head just simply doing nothing. So that's BERT. For machine translation models, people have found that sometimes the model just simply attains to the end of sequence token. And the model do that when it wants to ignore the contribution of the source sentence. This would usually happen when the model try to predict some functional word. Like I said, if we're just trying to say go to, then you don't really need to know what exactly happened in the source sentence, because to just naturally comes after go. Another case of model attending to end of sequence token is when it has hallucination. I'm not sure if the concept of hallucination is explained to you yet, but in short, is the phenomena when simply the machine translation output is completely irrelevant to the source input. So at least for machine translation. So as you can imagine, it's quite a harmful case, because then maybe the user would completely lose trust in these kind of models, because it just simply outputs something that is so irrelevant, so unexpected compared to what the input was. Yeah, and then usually when hallucination happen, people notice that the model pay the most attention to the end of sequence token. So yeah, if hallucination happen, then focus on end of sequence token. But we cannot infer the other way around. We cannot infer that if the model focus on the end of sequence token, then it's hallucinating because of other cases like this predict function word case. And then in some reasons, autoregressive LM like Llama or some recent large language model, many of the heads focus on the beginning of sentence token. And people have found that if we just simply remove this beginning of sentence token, then the performance degrades a lot. And they have shown that some early feedforward network in Llama 2, actually they gather all relevant information from the whole input sentence, and then just gather it and then write it into the residual stream of the beginning of sentence token. So it just happened to be selected to be the one that is going to gather all the information. And that's called attention sinks. Okay, and next we have this long list of what people have found in the feedforward network blocks. So as I mentioned before, maybe the neurons within the feedforward network blocks is already the most reliable ones, if you want to try to look for some features. So if you look at the input neurons, then you can see there's some positional range neurons that fires on specific position of the input. There's some skill neurons which fire on some specific tasks. Some concept-specific neurons which fires when some concept is presented. And then in the output neurons, then people have found knowledge neuron, linguistically acceptable neurons that promote linguistically acceptable prediction, neurons that try to output space and time format kind of output, language-specific neurons, token frequency neurons, and neurons that try to suppress improbable continuations, like trying to avoid the model just keep being stuck in the decoding loop and then output one repeated token until the end. But as I mentioned before, we also have this polysemantic problems. So people have seen that some neurons just detect the whole n-gram. So instead of focusing on one single position in the input, it tries to detect the whole block of input. And also, as I answered to the question before, there are many dead neurons as well that just simply never activated in certain stages. Okay, so I think that was all for the special patterns. Okay, the last thing I want to say is about the residual stream. I wasn't really able to fit it into somewhere that makes more sense, but I just want to make a quick note about this, is that in the residual stream, if you do next word prediction, you can imagine that when you go up the residual stream, the representation of the current token that just get input at some point after some stage in the residual stream, it will get slowly convert to the new token that you want to predict. So for example, if you have the sentence that I like, and then trying to predict something next, then the word I like and like mostly is going to be encoded in the beginning, embedded in the beginning. And then as you go up the residual stream, the model at some point will try to remove the information about this word like, and then slowly transform the word like to be closer to the representation of the word cat, for example, to output I like cat. So yes, so there should be some kind of transition within the residual stream. And I think this is something that you can inspect using the logic lens thing that I mentioned earlier, that just simply fit the intermediate representation into the embedding layer and see already what the model is doing at certain stage. Okay, so here are the sources that I have used. Most of this presentation is based on this huge survey paper. I think it's like 37 pages, not counting the references. So if you have any details that you want to know, I think this is a very good resource. I highly recommend. And then the other ones are shorter papers that contributes to some certain points that I make in this presentation. But yeah, the main source was this one survey paper. So yeah, that's it. And thank you for listening.